So next we will talk about some other details about the convolutional neural network. Okay, so here is our model. Okay, we talk about convolution pooling, and we use a flattened layer to perform classification, right? So here we have the code. So after we have the model, okay, the second part is the compile. As we mentioned, we need an optimizer so that it can help us to perform gradient descent with certain strategy. We'll talk about strategy later. Okay, the strategy is called Adam right now. Okay, and the second part is the metrics. Okay, in addition to, because it is a classification problem, we usually use cross entropy, right? But in addition to cross entropy, we ask the model to output its accuracy every time when it train the model. Okay, so the matrix accuracy, and the loss right here, you can see that it is very different. It's called sparse categorical cross entropy. In the previous example, okay, when we classify binary stuff, okay, we have yes or no, true or false, 0 or 1. We use binary cross entropy, right? But currently we have 10 different classes, so we need to use categorical cross entropy. But we have two versions of categorical cross entropy. The first one is called categorical cross entropy. The other is called sparse categorical cross entropy. These two loss functions are different. Okay, so for categorical cross entropy, okay, the y should be 1 hot. That means if you use certain data set, if you like to use categorical cross entropy, your y should be something like this. And you have to input all the 1 hot matrix to that categorical cross entropy. Okay, if your y, okay, looks like 1, 2, 3, it's an integer, and you should use sparse categorical cross entropy. Okay, you make sure you understand that, because it is very important. If you misuse this loss function, the result will be not what you expected. Okay. So again, there's a fit, right? We have the x, we have the y, we have 6,000 images as the x. Okay, we have the corresponding y. So right here, since we use sparse categorical cross entropy, so the y here is an integer. We have 60,000 images, so we have 60,000 integers to represent this category. Okay. The batch size is depend on your design. Okay, you can use 32 or some other value. Okay, the epoch right here is 5. Okay, so you still use 10% of the training data as the validation data to perform the validation. So after that, you can see the accuracy after the first epoch is 95%, 98, 99, 99, 99. Okay, the validation accuracy is 98, 98, 99, 99, 99, and here is the loss, which is the cross entropy. Okay, so basically you can simply just draw the picture, okay, to see the trend of those loss and accuracy. And as you can see that since the validation loss seems stable, maybe you can stop it right here. Okay, so and of course you can add more epoch in your training to see if the training accuracy will become lower or even higher, or you can see that. Okay, so again, we can perform prediction after you train the model. Okay, so given a new sample, okay, we randomly choose a sample from the test image. Okay, apparently it is a 4, right? So we put it into the model for prediction, and the result will be something like this one. Okay, and you can see that since we perform softmax, right? So we have 10 different numbers for each category. And you can see that this number is the largest one, okay, because it's minus. Okay, it's a very small value. So basically it indicated after the prediction of the model, it is 4. This image is 4. Okay, and I would like to mention something very important. Maybe you did not notice that is this one. That is a very important thing. Take a look at our model, okay? It's right here. And as you can see that sorry, as you can see that after the convolution, okay, we have additional layers right here, okay? That is the flattened layer. So we can flatten all the neurons on all kernels, right? So in total, we have 3,136 different neurons, okay? And we have 2 additional dense layers. Okay, the one is 128, the other is Y. Okay, we have 10 different. And you can see that we still have activation function on that 128 hidden neurons, but we don't have any activation functions on the dense layer. Okay, we don't have that. And as I mentioned before, usually we put a softmax as the activation functions right here. But in this example provided by Google, they did not do so. That is because, okay, there's a very important things right here. In the loss function, okay, there is a parameter called from logit. Okay, and if you do not have softmax in your network model, you can put the softmax in your loss function, which is from logit equals true. The true will perform softmax when it calculates its cross entropy. Okay, that is a weird setting, but it is how everybody does. Okay, so if you don't have softmax right here, you have to put log from logit equals 2 in your loss function. Okay, so on the other hand, if you put softmax right here as your activation function on the output layer, then you don't have to specify from logit. So you have to write from logit equals false on your loss function. It is weird, but that is how it works. So when you do prediction does not need to go through the loss function, right? It only goes through the model. So after that, you have to perform softmax by yourself to obtain the result of after softmax. Okay, that is a little bit weird, but you have to notice that. That is how everybody does. Okay, so after that, okay, I want to introduce 2 additional layers, 2 additional things. Okay, the first one is we'll talk about shuffle. Okay, that means when you perform gradient descent, you need to shuffle the training data before every epoch. Okay, so that is shuffle. Okay, we talked about before. The next thing is output. Okay, you can see that we add an additional layer, which is called drop out after max pooling before flatten. The 0.2 means that when if there's some neuron right here, if we apply drop out, okay, so when the neuron output to the next layer, okay, there are 20% of the chance, that is 0.2, the definition, 20% of the neuron will not output data to the next layer, and it is performed randomly. So that is means 20% of the neuron will be turned off. So the output will be 0, 20% of data. So for the next layer, okay, for the next layer, only 80% of the data will be passed through the dropout layer, and only part of the data will be passed to the next layer. That means only partial information will be passed to the next layer. That is called dropout. The reason why we use dropout in our neural network is because that sometimes, okay, some neurons, okay, are so strong. That means you don't need those hidden neurons to collect information from the previous layer. Okay, and maybe their weight are so small. So when we collect information from the previous neurons from the previous layer, those neurons, they are we use some we use dead or die, okay, dead, to describe such kind of things. Those neurons are useless because some neurons are so strong. They can characterize very important features. Okay, so P1 neuron will only depend on some strong neurons, and some neurons are weak. Okay, if we randomly drop some values from some random neurons, so it is possible that for some training, okay, H1 and H2, these two strong neurons will not output value. So that means P1 need to collect information from H3 and H4. Those are weak neurons. But if you do so, if we do drop out, those neurons, after, when we perform gradient descent, those neurons will become stronger. Okay, we use this word stronger. Try to collect as more information as possible to make itself, which is H3 and H4, become stronger, so that it can provide useful information for P1. That is how we use such kind of a random dropout design to make every node, every neuron, okay, be stronger. Okay, because P has activation, which is okay. So if we have information from H1, H2, and H3 and H4, they are both strong, and H1 is okay. We have an activation function, so it will still output a very large number, even if some neuron is randomly dropped out or is dead. It's okay because we still have some other strong neurons to provide enough information for P1 to be activated. Okay, that is a very common design, so make sure you have such kind of dropout in your neural network. And again, even if you drop 20% of the neuron, the accuracy still looks good, right? So that is the first design. The second additional design is called early stop. Okay, we talked about callbacks before. Every time, for example, we have, I think there's 23. Okay, 20 epochs. I think that is 5 or 20. Okay, 20. So if epoch is 20, that means we have 20 different epochs, and for each epoch, okay, and we have some many batch, right? So for each epoch, we have 1,688 different many batches. That is because we have total 60,000 samples, right? And the batch number should be 32. So that is this number. So we can do partial differentiation 1,688 different times when we perform gradient descent, right? So after each epoch, okay, the callbacks, it is a list. It means after each epoch, what additional process we should do, okay? So we should do listing, that is early stopping, okay? As you can see that, let's take a look, as you can see that, maybe after 10 epochs, you know, the trending loss becomes stable and the validation loss becomes stable as well. So even if we have 20 epochs, but actually you don't have to spend that much time. You can stop at the 10th epoch, right? You don't have to spend times to search lower cross entropy or lower MAC value, but because it really doesn't matter, because the model becomes stable after 10 epochs. But actually we don't know when should we stop. So here is a callback function called early stopping. That means we need to monitor something, okay? So you can monitor loss, which is the cross entropy right here, or you can monitor accuracy, monitor validation accuracy, or monitor validation loss, which is okay. Okay, so the patience 3 means 3 epochs. Within 3 epochs, if the value of your monitor, which is validation accuracy, okay, does not decrease, okay, so that is the minimal change of your monitor. That means if your model does not improve within a time window of 3 epochs, so the monitor is validation accuracy and the threshold is 0.0005. That means your model may not improve later. So you can start right here. You don't have to perform additional epoch. So in this case, although the epoch right here is 20, but you can see that it stops at the 5th epoch, because the validation accuracy is right here, okay, will not improved. So that is, so basically, although we don't know how many epoch we should perform, but you can write it, for example, 100 and 200. But you can also add early stop in your training, so it will stop automatically. No matter your entire epoch is 20, 200 and 100, no matter, it will automatically stop. Okay, so that is early stop. So it is very useful. Again, you only need 5 epochs. Okay, so that is okay. So the next thing is a layer. So I strongly recommend you take a look at the definition of a layer. We have several different. We talk about filters, kernel size, stride, padding, activation, and some other things. But I strongly recommend you take a look at this web page and try to figure out what is the additional parameters of a layer. Not only the convolution, also the dense layer. So make sure you understand what exactly those parameters means, and it may be helpful for you to create a better network structure. Okay, so that is the definition of initializer, regularization. Make sure you take a look at these web pages. Okay, the next thing I'd like to talk about is the intermediate layer. Okay, we mentioned it before. For your model, you can always get a layer by its name, and you can print the weights out. So here, as I mentioned before, although we don't know what exactly those kernel, although we don't know what exactly a kernel will be, but after training, we can print them. Okay, and so here is the result. Okay, so I write a function to print all of the kernels at the first convolution layer. In total we have 32 different kernels, so that is the kernels. So as we mentioned, those kernels, okay, those kernels will be used to go through the entire input value. It seems like the kernel is trying to find some patterns, and if the patterns, if they match some patterns right here, the value right here will be high, right? So that is the result. That's the first kernel to the 32nd kernel. But after that, you can see that actually we don't know what exactly those kernels trying to figure out. Those are patterns, but we don't know why those kernels use these patterns to search the entire image and output the hidden neuron. So that could be the problem. But the idea is that the kernel, the optimized kernel, which is exactly the kernel we shown right here, but we don't know why our neural network use this kernel as the optimized kernel to perform the prediction, the handwriting prediction. Okay, you can taste by yourself. Okay, so if we go through the for example, that is the first test data. Okay, we have 10,000 images in testing, right? And we have 32 different kernels. You can change the number by yourself. And as we can see that if you use the number 8 kernel and the number 0 images, and the result of after first convolution, the result will be this. So this part stands out because they are bright white colors, and that is not the black color. That is not what this kernel, the number 8 kernel, trying to figure out. So in this case, we can see that maybe this kernel is trying to figure out some straight line right here, but that is what we guess. It is simply a guess. Okay, so that is. And if you are interested in kernel, you can take a look at those kernels. Okay, right here are human design kernels. If you apply some kernels on original image, and the result will be this, and this. And you can see some kernels will blur the original image, and some kernel will sharpen the image, and some kernel will, we have several different results. But those kernels are designed by human beings, not AI. But this kernel, those 32 kernels are trained by AI, and that is the result. Okay, so that is convolution. Okay, we stop right here, and we'll continue next topic in the next video.